I'll start from a comment made by Chris in his wonderful talk. He said that, the solvers, they can make many arbitrary choices, and these arbitrary choices can have huge impact on the performance of the solver. And this actually brings me to the use of machine learning in solvers in general. And the big takeaway of my talk is that machine learning is a powerful way of determining these arbitrary choices that he talked about. So, um, so with that, let me kind of go into the talk, and I think I don't have to contextualize and motivate too much about SAT for this community, because you probably have been using SAT solvers in some way, shape, or form, or extending SAT solvers. So I'll probably kind of skip over that a little bit here and kind of focus on one of the most important questions in SAT solving, which is why on earth do these solvers work as well as they do? Even though the problem they're addressing is NP complete, and we believe that this problem is hard in general, right? So there is a clear gap between practice and complexity theory in its ability to explain why SAT solvers are efficient at all. And is there a principled way in which we can address this question from a theoretical point of view, but at the same time, can that principled understanding also lead to a better design of SAT solvers? As you well know, SAT solvers are today a soup of heuristics, and it's really hard to kind of figure out which heuristic is really responsible for the power of the solvers. I mean, there are some basic heuristics, but beyond that, like what are the heuristics that really enable the solver to be efficient? And I'll address that question here. So very, very quickly, what's the SAT problem? So given Boolean formulas in conjunctive normal form, decide whether they are satisfiable. Skip over that very quickly. And just very quickly remind you of the architecture of the modern SAT solver. So it takes this input of Boolean formula, performs Boolean constraint propagation, which I'm sure you're familiar with. And then if it is able to come up, if the state of the solver is not in conflict, meaning that the current partial assignment as applied to the formula is not unsatisfying for that formula, then what the BCP would then check is, well, have all the variables been assigned? If all the variables have been assigned, it returns SAT. Otherwise, it uses some magic procedure to pick a variable and gives it a value and adds it to the queue of kind of the unit variables that it has, which the BCP subroutine would use to do additional propagations. If there is indeed a conflict, then a conflict analysis is performed, and a conflict clause is learned as a consequence. There is a back jump that occurs, and the solver continues in this process. So kind of the question that I asked a few years ago was, is there a way I can abstract this so that I have a better understanding conceptually of what's really going on without necessarily worrying about too many of the heuristics? And this led me to this idea that the best way to think about solvers is through the lens of proof systems. Now, I'm not obviously the first person to think about solvers as proof systems. Many people have thought about solvers as proof systems, but almost all of that work has been from a purely theoretical point of view. What I realized was that if you were to view the solver as a proof system, then there is a very natural way in which you can actually bring machine learning into the picture. So what is that natural way? So you could view a solver as a combination of proof system and machine learning as follows. What the solver is really doing is, in fact, you can think of a SAT solver as an optimization procedure. So there are subroutines in the solver that are trying to optimize the construction of a proof. And even if then the input formula is satisfiable, technically solvers are actually constructing proofs of the parts that don't have any solutions. So what does it mean to construct a proof optimally? What it means is you want to sequence these proof rules that you apply in an optimal way, select the most appropriate proof rules that would minimize the size of the proof that you're constructing. And fortunately, solvers actually produce a lot of data. And given that this is an optimization problem, um, please, given that this is an optimization problem, we can address this via machine learning methods that optimally sequence and select proof rules. So one particular heuristic that we can focus on here is the branching heuristic. Prior work in the context of branching heuristic kind of viewed it essentially as a dynamic ranking function that ranks variables in an input formula in some order. And it wasn't quite clear what this branching heuristic was really up to. What was the optimization or what's the objective function that it was trying to optimize? All we knew was that there were a variety of branching heuristics, and the branching heuristic that were really good were ones that kind of dynamically ranked and re-ranked variables in the input formula at regular intervals throughout the run of the solver. And this was kind of where the understanding of the famous vis-a-vis branching heuristic was. And I personally found that to be unsatisfactory. So over a period of last several years, we studied 7 of the most well-known branching heuristics in detail and kind of started viewing the branching heuristics as prediction engines that attempt to maximize some objective function. And the objective function that we found to be most relevant in the setting was what we refer to as global learning rate that I'll define in a minute. And this in turn led us to devise a new machine learning based branching called LRB that for the first time was able to match and actually beat the famous vis-a-vis branching heuristic that has been part of most SAT solvers for the last several years. So again, going back to the view of the SAT solver, you can think of, if you can see my cursor here, you can think of the SAT solver as having kind of 2 loops here. There is one loop here where you have a propagate followed by a conflict check, followed by whether all variables have been assigned and a branch. And there is this loop between the BCP and branching. And then there is another loop where you have BCP followed by conflict analysis and backjump, etc. You can kind of abstract this as follows. You can think of this as a student and a teacher process. There are 2 processes inside the SAT solver, or an agent and environment. And the agent is basically making choices, the decision heuristic, propagating them. And when the agent has a partial assignment that is not satisfying for the input formula, it queries the environment or the teacher and asks for the reason as to why this is not satisfying. And the teacher rewards with a learn clause. And depending on the choices you make, the reward could be different. But the goal here for the agent is to learn possibly the best learned clause that it can learn based on the choices it has made. So this is very reminiscent of reinforcement learning. And it was very natural then to kind of dig into reinforcement learning literature and then use that knowledge to come up with better branching heuristic. And so the very first goal here was to define a good objective or reward metric. And one particular objective function that we found to be very useful was this global learning rate idea, which is essentially the way we define it is through the run of the solver for a particular instance is the total number of conflicts generated divided by the number of decisions. And the idea of trying to optimize this particular objective function makes sense because in any proof, what you want to do is you want to minimize the number of assumptions you want to make or the number of case splits you have. So you want to minimize the number of decisions and you want to maximize the number of conflicts because that corresponds to learning lemmas about the search space of the formula. And after searching over many different kinds of objective function, we found this one to be the best one. Okay, so now that we have made a connection, at least at a very high level, between what's going on inside the SAT solver, namely that it's a proof system, the reasoning, the symbolic reasoning is being done by clause learning and BCP, plus machine learning methods. In particular, you can view it in terms of reinforcement learning. So the next kind of immediate question was, what would be a good problem whose solutions we can adapt to the SAT setting? So we have to kind of do a mapping between that problem and what's going on in SAT, even if if the mapping is not perfect, we can still kind of leverage some of the ideas from that setting to the SAT setting. So the particular problem we zeroed in on was perhaps one of the most basic reinforcement learning problem called the multi-arm bandit problem. And it's a very kind of simple problem. And the idea there is that there is a bandit, which is a slot machine, and there is a gambler, which is the agent, and the slot machine is the environment. And the goal of the gambler is to maximize their return. So they have to play the slot machine for some amount of time and maximize their return. Every time they play the slot machine, it's like they're taking an action, and in return, they get a reward. And in this case, if there is just one slot machine, there's not much to think about, but the problem becomes really interesting in the following scenarios. You have many slot machines to choose from, and further, the probability distribution of your rewards is non-stationary, means that it changes over time. So you have several slot machines, and the probability distribution is changing over time. So what is a good strategy that a gambler can take in order to maximize their reward? Now, you can imagine many different kinds of strategies. One could be that they try all possible slot machines, but if there are too many of them, that's probably not a good idea. They will run out of resources very quickly. So usually what they do is randomly pick some subset and play with those, and then zero in on one that gives you the maximum reward. But how do you determine which one is giving you the maximum reward over a period of time? There are many ways to do that, but perhaps in the non-stationary setting where the rewards can change over time, perhaps the best strategy is what is known as the exponential recency weighted average method. And the idea is extremely simple. It's just that, think of it this way: the gambler is maintaining or keeping track of a time series with respect to every slot machine they play. So every time they play a slot machine, they keep track of how much reward they got. And then they can then analyze that history and try to figure out which of those slot machine is going to give them better reward going forward. They can do that by analyzing the trend and zeroing in on that slot machine. And usually, if the behavior of the slot machine doesn't change too much very quickly, then chances are that the one that has been behaving well in recent time would also continue to give you rewards in the future. And one way to implement this idea is through using an exponential moving average as opposed to a sample average, where the sample average just tells you the return on the entire time series, but the exponential moving average gives higher weight to recent rewards and less weight to rewards from the past. And by doing so, you can kind of figure out the machine that gives you the best trend. So kind of taking this analogy one step further, so on the left side of this slide, you have the slot machine. You're keeping track of the rewards over time, and the gambler is then focusing, uses the exponential recency weighted average method to come up with a ranking of which machine is giving the highest reward in quote unquote the recent time window, and then predicting that will continue to give rewards in the near future. And if it so happens that that slot machine doesn't give you as much reward in the near future, over time, the exponential recency weighted average method guarantees that the ranking will dynamically change over time. So the mapping to SAT here is that every slot machine then corresponds to a Boolean variable in our setting, and the reward instead of money is learned clauses, and we keep track of how many learned clauses we get due to these variables. And this concept of due to a variable can be realized in many different ways. It could be that branching on that variable led to a conflict, or that variable appeared in conflict analysis, or there could be many different ways you can define that. And there are some big differences between these two models. So for example, typically slot machines are not dependent on each other, whereas variables are. So this analogy is not perfect, but still it is, at least experimentally, we were able to show that when we lifted the method from the MAB setting to the branching setting, we got very good results. So now to dig a bit deeper into the branching heuristic, which we call learning rate branching, here is how it works. So we have on the slide these circles that represent time, and for every variable between the time the variable gets assigned to the time that the variable gets unassigned, we keep track of how many times it appears in a conflict, or better yet, maybe in a conflict analysis. And that tells us, so in this case, for example, this variable A appeared twice in out of 3 conflict clauses that were learned. So the sample learning rate corresponding to this variable at these 3 time steps is 2/3. Similarly, again, when it gets assigned to unassigned, we generate another data point. So now you have a time series corresponding to this particular variable. These are the rewards. And then we compute the exponential moving average, where the learning rate in the near future, near past, gets higher weight than in the distant past. So using this method, we implemented this method with MiniSat, and this was back in 2016, 2017. And since then, a large number of SAT solvers have used our method. And in fact, up until this year's competition, most of the winners, most of the solvers that won either gold, silver, or bronze in the SAT competition used a variant of the MapleSat solver, which is the solver that I'm presenting right now. So we took MiniSat with vis-a-vis, which is what it comes shipped with automatic, like by default, and we replaced vis-a-vis with another heuristic that we came up with called CHP, and also LRB. So this is the cactus plot here, and as you well know, a solver that is more to the right and lower in this plot is better. So there are 3 solvers plotted here, 3 performances of 3 solvers. The blue one is vis-a-vis, MiniSat with vis-a-vis. The green one is MiniSat with CHP, and the brown one is MiniSat with LRB. And the first time we implemented this, we were able to solve 100 more instances from the SAT competition than MiniSat with vis-a-vis. So we already knew that we had something very interesting on our hands. So in summary, we were able to view branching heuristic as a machine learning method whose goal is to optimize sequencing of unit resolution rule applications, because that's kind of what the heuristic is enabling you to do. And reinforcement learning is a powerful way to model these heuristics. Agents in reinforcement learning correspond to branching heuristics. And we didn't stop there. We were able to show that we can lift this lesson to many other aspects of a solver, not just branching heuristics. So since 2016, 2017, we have designed about 7 different heuristics to improve solver performance, including a machine learning-based restart method, machine learning-based splitting heuristics, machine learning-based initialization methods, and so on and so forth. We did additional experiments to cross-check whether or not global learning rate is indeed a good metric. That is to say, the branching heuristics whose global learning rate is the highest also is the one that corresponds to the one that performs the best on the SAT competition benchmarks. We've made several other findings actually as we studied branching heuristic during this period of time. We found that SAT solver branching heuristics like vis-a-vis and LRB tend to have a very localized behavior. That is, they tend to zero in on a small part of the set of constraints, try to get as many conflicts as possible over that set of constraints, and then over time move on to other parts of the formula. So this is kind of the exploitation versus exploration analogy from reinforcement learning, where you kind of try to explore a part, and then if there is rewards in here, they exploit it, and then you move away from it when the rewards start decaying out, going down over time. And this also suggests that the way to beat these heuristics is to use formulas that force the solver to do global reasoning. And then this method, or formulas that necessarily require global reasoning in order to be solved easily, then this particular method of local reasoning will not work. In fact, we leveraged this concept recently to prove some theorems where we showed that lower bounds for vis-a-vis in a paper in SAT 2020. So kind of the basic takeaway of my talk is this idea that solvers are a combination of proof systems and ML-based optimization procedures is a very general idea. And you can use it in not only from the context of SAT, not only to improve how SAT solvers sequence, select, and initialize proof rules, not only in the context of Boolean satisfiability, but in many other contexts. And many other people also have been looking at this idea from the point of view of provers in first order provers, higher order provers, and as well as SMT solvers. So here is a list of the various heuristics that we have developed, machine learning based heuristics, both for SAT and SMT. And the final point I would stop with is that I started by saying I wanted to get a better understanding of how solvers work. And this is just one step in that direction. I think we don't yet fully understand why SAT solvers work well. In order to be able to pull that off, we have to go through the proof complexity route and kind of try to understand the structure of industrial instances. Why is it that, what is it special about the structure of industrial instances that distinguish them from random instances and crafted instances? And further, what is it about this structure that the solver is exploiting? There are many clues we have right now. And the end goal here would be to have a proof complexity theoretic result that establish an upper bound that uses this structure, and lower bound for instances that don't have this structure. So lower bound for classes of instances that don't have this structure. So with that, I will end my talk and take questions. Thank you for your attention.
All right, thanks, Vijay, for a great talk. Applause. All right, are there any questions? Yes, go ahead, Chris.
All right, so Vijay, thanks so much. That was really, really interesting, and definitely gets you thinking about all sorts of things. So the question that I have is that I could be wrong, but it seems to me like in sort of the longer history of SAT solving, there was this recognized trade-off between the branching heuristic and the cost to store information, right? So that something like keeping track of how many clauses were, as yet unsatisfied or something like that is not a good idea, because it just takes too much time to keep track of it. So it's not that the information isn't useful, it's just that that information is inefficient to keep track of. So the vis-a-vis thing, it's not just a good heuristic, it's also a heuristic that you can keep track of the necessary information very efficiently. So if you're using machine learning, there's always the possibility that you could throw in some other features, right? Extra information that could also be kept track of efficiently. And so I was just wondering if you've thought of any extra information that sort of has that property that it doesn't cost much to keep track of it, and maybe it'll help, whether you've thought about adding that into the learning.
Yeah, actually, I just attended a PhD thesis where they use a concept called centrality. And they use this, so you can take a graph theoretic representation of a formula, and then you can compute various different centrality measures over the variables of that of the formula with respect to the graph theoretic representation. And variables that tend to be highly central, if you were to branch on those first early in the search, that can give you a benefit. And this information can be computed relatively cheaply. I mean, it is obviously more expensive, way more expensive than the information that vis-a-vis keeps track of, or LRB. But still, this is something you can keep track of relatively cheaply and leverage to come up with a better branching heuristic on top of vis-a-vis. So that's, it's not like replacing vis-a-vis or LRB, but it's like augmenting vis-a-vis or LRB. And I think that's one answer. And generally speaking, the question, if I were to generalize your question further, is that how can we explicitly exploit structure? Let me put it that way. Is there a way for us to explicitly exploit structure. We know that CDCL somehow implicitly exploits structure and does so very well. Can we do it in a much more explicit way? There has been a lot of work in community structure as well, which is a different graph theoretic representation of Boolean formulas, and then using that information to either help partition the formula or come up with a better definition of quality of conflict clauses. So I published a paper to this effect in 2020 for a parallel SAT solver, where you have to make a decision on which clauses to share among the various cores of a parallel SAT solver, because you produce so many clauses, so you have to kind of prune that out. And the traditional method was like LBD based. I'm assuming you know what LBD is. So it's basically talks about the number of decision levels in a clause at the time the clause was generated. And if the lower the LBD, the better the clauses. In the community structure setting, what you can do is you can say, okay, I take a formula, I decompose it into this community structure. And conceptually, the idea of community structure is you want a decomposition of the graph of the formula such that there are more internal connection between the communities than outgoing to other parts. So it kind of suggests that divide and conquer would work well if the community structure has this highly decomposed structure to it, highly decomposed property to it. And now imagine that you have clauses that span many different communities, right? So you can learn a clause where each of the variables in the clause that you learn happens to span, say, 5 communities or 10 different communities. So what we found was the larger the span of the clauses, the worse such a conflict clause was. And the smaller the span of the clause, the better it was, at least within the context of industrial instances. So this again suggests that local reasoning is good. And if you are able to somehow leverage kind of the locality in the formula and do so dynamically, that's actually better. So those are 2 instances of how people have leveraged structure in the context of SAT.
Thank you.